So now we are learning about the Hull cutoff magnetic field equation or the critical magnetic field equation, which is denoted by BOC. That is nothing but the magnetic field at which the electrons coming out of the cathode just gazes the anode, or it touches the anode and then comes back. The figure which we are going to look into is the same figure of the cylindrical magnetron. Center we have the cathode, which is having a radius A. That is what is shown here also. It is having a radius A. And around it we have the anode, which is having so many slots. It is having slots, and each of the slots are acting as a resonant cavities, which is producing the RF signals or the noises. And the cathode is connected to minus terminal of the beam voltage V0. Anode is connected to the positive terminal of V0. And when we are connecting this voltage like this, we know that we'll be having an electric field from which is direction from what? Plus to minus. So the electric field is from plus to minus, and that is indicated by ER because it is in radial direction, or it is along the plane of the paper. So electric field is along this radial direction ER, and we know that the magnetic field, since it is a crossed field device, the magnetic field is applied in perpendicular direction, that is B0. That is what is shown here. And we are considering that for the derivation, since V0 is applied between the anode cathode, since it is a negative potential, we are assuming that the potential at the cathode is equal to 0, and hence what happens? All of the V0 is being applied or being present in the anode section. And here we cannot use the normal Cartesian coordinate system. Here instead we are using the cylindrical coordinate system, because the electrons, they are not moving in a straight path, they are taking a curved path. So we have to take the cylindrical coordinate system here. So cylindrical coordinate system, we are taking what? R, that is the linear distance we are taking. Along with that we are taking the angular distance theta as well as the Z distance. R, theta and Z are the coordinates that we are considering in the cylindrical coordinate system. And we know that linear velocity is equal to distance by time, or we are saying it as what? ds, or we will be taking it as dr divided by dt. That is, the velocity is equal to distance by time. Here if the distance is r, we take it as dr by dt. And now what is the angular velocity? So for that we want to know what is the angular displacement. So this is the angular displacement. How to get this value? This value, let it be taken as S. How to get the angular displacement is, let this be equal to theta, and we are taking what is tan theta? Tan theta is equal to, we are taking the slope, tan theta is equal to S divided by, from the diagram, S divided by R, where R is the radius. Tan can be avoided, or we can write what is the value for S. S is equal to R theta. So the angular displacement is equal to R into theta. Angular displacement is R into theta. So what is the angular velocity? Angular velocity is equal to R into d theta by dt. R into d theta by dt. So this is the thing that is related to the cylindrical coordinate system. So moving on to our derivation. We know that the force which is acting on the electrons which is coming out of the cathode, it is consisting of two parts. The first one is, it is having the force due to the applied electric field. That is, the force due to applied electric field, we can say it as charge of the particle into the electric field applied. That is E. It is minus, since charge of the electron is negative, minus E into E plus the force due to the magnetic field. What is force due to the magnetic field? Again, it is charge into V cross B. It is a vector product. V is the velocity and B is the magnetic field applied. So the first step is the force due to electrons. So the force acting on the electrons is equal to force of electric field plus magnetic field. Force of electric field is equal to charge into applied electric field. Force of the magnetic field is equal to charge into V cross B, and is a vector product. E is nothing but the applied magnetic field. V is the velocity of the electrons. B is the applied magnetic field. E is nothing but the charge of the electrons. Since it is negative charge, we are taking a minus sign. And then the same thing we are going to be rewriting it. Let that be equation number 1. We are rewriting it. So the force is equal to, the force can be again rewritten as Since there is only electric field in the radial direction, we can write minus of E. E is common in both the terms. So minus, I'm taking it outside. Minus E into ER. Why did I take minus? As we know that the electric field is from what? Plus to minus. That is from anode to cathode. That is this direction. But we are taking the opposite direction. That is why we are taking this minus ER here. Since the direction of ER is anode to cathode, that is the opposite direction, the electrons are moving from what? Cathode to anode. That is why I have represented it by a minus sign, minus ER, plus V cross B. And again, what is this force? Force is equal to mass into, we know that force is equal to mass into acceleration. Force is equal to mass into acceleration. That is ma is equal to the same equation, minus E into minus ER plus V cross B. Again, from this, what is A? A is equal to minus E by M minus ER plus V cross B. Now we have to find V cross B. What is V cross B? Cylindrical coordinate system. So it is along R, theta and Z. So here instead of theta we are taking phi. So AR, A phi and AZ. So we have to take the velocity, velocity and the magnetic field along the R, phi as well as Z direction. So what is the velocity along the radial? Velocity is equal to displacement by time, as we have already indicated. So what is that? dr divided by dt. What is the angular displacement? As we have seen earlier, it is equal to r into, earlier we have seen it is r d theta by dt. Here we have taken, since it is phi, r d phi by dt. And a is z. We do not have velocity in z direction, but because electrons are not moving in a z direction, so that is why we have indicated a z is equal to 0. So that is related to the velocity parameters. Similarly, we can say that we can take the magnetic field. We know that magnetic field is not present along the radial as well as in the phi direction. There is magnetic field only along the z direction. That is why we have taken Bz. So now taking the vector product, that is equal to AR. We are taking vector product AR into R d phi by dt into dz. That is what is written here, R bz d phi by dt minus what is the next term? A phi into what is the next term? Bz into dr by dt minus 0. And similarly the third term, if you are taking the third term, we can take Az into, if you are taking Az into, anyway this is 0, this is 0, this is also 0, so we don't have that Az term there. So we have got the V cross B. Now we have to put that V cross B in equation number 2. So putting that in equation number 2, we'll be getting A is equal to minus E by M minus ER. Earlier we have simply written as minus ER, but since we are representing it in the radial direction, that is why we have included the term AR here. AR, which is just representing that it is along the radial direction, plus what we have got just now, V cross B. The same thing we are just reproducing here. Whatever we have got as V cross B, the same term is being represented in this equation. That is equation number 3. And we know that in a cylindrical coordinate system, the acceleration is already having a permanent equation which is equal to AR d square r by dt square minus r d phi by dt the whole square plus A phi into 1 by r d by dt r square d phi by dt. That is equation number 4, which is according to the cylindrical coordinate system. So we know that 3 and 4 is both the equations for acceleration, and then we are going to be comparing both the equations. We can see that since both these equations are the same, what will happen? AR term of both these equations should be the same. Similarly, A phi term of both these equations should be, the coordinates of A phi term should be also the same. So equating those two things, we'll be getting, what are the AR terms? I'm taking the AR terms together in this equation. The AR term is d square r by dt square minus r d phi by dt the whole square will be equal to, what are the AR terms here? Minus E by M into minus ER. That is minus into minus is plus E by M ER. Then we are having one more term, that is this term. That is again minus E by M. We should not forget this, minus E by M R BZ d phi by dt. It is equation number 5, which we have obtained by equating the AR coefficients. The next we have to equate the A phi coefficients. So equating the A phi coefficients, what you will be getting? A phi coefficient is, here it is in the cylindrical coordinate system, it is 1 by R. So it is 1 by R d by dt R square d phi by dt is equal to, what is this allowed here? It is minus into minus E by M, that is equal to what? Plus E by M into BZ dr by dt. That is equation number 5 and 6. That is what we have done is, we have taken the equation for acceleration from the equation, that is F is equal to, the total force is equal to electric field plus magnetic field. That we have simplified and we have obtained the equation for acceleration. That is one first step. The second step is, according to the cylindrical coordinate system, we have an equation for the acceleration. That is the second one. Then we have compared the AR terms and A phi terms together, and then we have rewritten the equations as 5 and 6. Now what we are taking is, we are taking the equation number 6 alone. We are taking the equation 6 alone, and in that, this is equation number 6, and in that E by M BZ, which that term E by M into BZ, we are representing it with a different term, that is equal to omega C, where omega C is called as the cyclotron angular frequency. Please remember this term, E by M BZ is denoted by omega C, which is called as the cyclotron angular frequency. So the same equation can be rewritten as d by dt R square d phi by dt is equal to omega C into R dr by dt. Now what we are doing is, we are integrating both the sides with respect to t, because we are having a differential term on both the sides. So we are going to be integrating to avoid that. Integrating both the side with respect to time, what will be getting? With respect to dt, we are integrating. So we'll be getting it as integral with respect to dt. So dt and dt here we are getting cancelled. Integrating with respect to dt, these both are getting cancelled. Here also dt and dt we are getting cancelled. Omega c is considered a constant because E is a constant, charge of the electron, M is mass of the electron, Bz is the applied magnetic field. So it is a constant, so we are taking it outside. So what is the remaining formula? That is equal to integral of this function is equal to what? R square. It is equal to R square d phi by dt. That is the first one. Integral of this term is, the integral of this term is R square d phi by dt, and what is integral of R dr? It is equal to R square by 2. It is equal to R square by 2. That is R square d phi by dt is equal to omega c into R square by 2. So we cannot keep it as such. Since we are integrating, there should be a constant coming, and let that constant be equal to k1. So now what is the next step? We have to find what is the equation for k1. So to find the constants, we have to apply the boundary condition. So what are the boundary conditions? The radius is equal to A and R is equal to B. So these two are the boundary condition. So let us start with at R is equal to A. What is R is equal to A? That is, it is the radius of the cathode. The electrons are in the cathode. D phi by dt is equal to 0. That is what? There is no angular displacement because they have not come out of the cathode. So angular displacement d phi by dt is equal to 0. So apply that point in equation number 7 because our aim is to find the value for k1. So applying that, what will be getting? Instead of R, we are writing it as A. So that is equal to what? We are writing it as A. And what is d phi by dt? D phi by dt is equal to 0. So what will be getting? 0 is equal to omega c R square. Instead of R square, it is A square by 2 plus k1. So what is the value of k1? K1 is equal to minus of omega c A square by 2. That is equation number 8. Then what should be the next step? Substitute k1 in equation number 7. So you will be getting R square d phi by dt is equal to omega c R square by 2 minus omega c A square by 2. Or again we can write it as what? Half. the half is common, half omega c into r square minus a square. And again, what is d phi by dt? D phi by dt is equal to half omega c. This r square is... So we have put equation number 8 in equation number 7, and we have obtained r square d phi by dt is equal to 1 by 2 omega c into r square by a square. Now we can do this. We can take r square to the other side. So putting it to this side, this comes in the denominator divided by r square. So what is r square by r square? It is 1 minus a square by r square. That is equation number 9. Now final aim is to obtain the equation for critical magnetic field or Hall cutoff magnetic field. So for that, the velocity of the outcoming electrons is equal to V0 is equal to V0 by m, where V0 is the beam voltage, small letter V0 is the velocity, or in general we can write small letter v is equal to root of 2v v by m. This small letter v is velocity, this capital letter v is standing for the DC bias. But we know the electrons are not moving in a straight line alone, they are also taking a curved path. So they are having both radial motion as well as angular motion. So the total velocity can be rewritten as root of Vr square plus V phi square. What we can write, that is the equation. This equation, V square becomes what? 2V V by m is equal to Vr square plus V phi square. Now what is this Vr? Velocity along the radial direction. V phi is velocity along the angular direction. What is velocity along the radial direction? We can write it as, it is equal to dr by dt. Velocity along the radial direction is dr by dt, and velocity along the angular direction is r d phi by dt. Now we are going to be taking the condition as at r is equal, because finally we have to derive at the critical magnetic field. What is critical magnetic field? The electron is just touching the anode. So at that point, what is the radius? Radius is equal to b. What will be the voltage that we have already seen earlier? The voltage we are considering as cathode, it is 0, and the anode point, it is the whole voltage V0 itself. So at radius b, the voltage is V0 itself. What is dr by dt? Dr is nothing but the radial velocity, because when the electrons are reaching the anode, it is having 0 velocity. That is why we have written dr by dt is equal to 0. And at that point, the magnetic field we call it as the critical magnetic field BOC. So applying all those things to equation number 10, we get what? 2E V by m is equal to dr by dt becomes what? 0, plus r becomes what? B, d phi by dt. Instead of this d phi by dt, we are going to be replacing it with equation number 9. That is what we are doing in the next term. So substituting 2v0 by m is equal to this first term becomes 0. First term becomes 0. Second terms, we are going to be replacing the equation for d phi by dt, and it all comes below the square term, and the radius is b. So again applying 2ev0 by m is equal to b square, applying the square, b square omega c square divided by 2 square is 4, 1 minus a square by b square, the whole square. Again taking 2ev0 by m is equal to b square. What is this omega c? Omega c is the cyclotron angular frequency, which is given by e by m into bz, the whole square. Omega c is e by m into bz. So replacing this, we get this term, and now we have to get the value for bz alone. So what is bz? We can write bz square is equal to 4 2s are 8 ev0 by m. B square comes to the denominator, e square also comes below to the denominator, n square goes to the numerator, this comes to the denominator. So 1 minus a square by b square, the whole square. There was an e and m term here and here also. So here one e by m cancels, and e by m here also it cancels. So the remaining term is what we get, bz square is equal to this equation, and the corresponding bz is nothing but the Hall critical magnetic field. Or what is this BOC or B0C? B0C is equal to the root of all these terms, that is what is given by this equation. And we can also write from the same equation that when the magnetic field is Hall critical field, the corresponding voltage is also called as the critical voltage. The corresponding equation for voltage is also called as the Hall cutoff voltage equation. So from this again replacing the same 11th equation, we are replacing to get the value for VOC. Instead of this V0, we are writing VOC is equal to, again simply rearranging, VOC becomes B0 square B square E into 1 minus A square by B square the whole square divided by 8M.